Welcome to lesson 3, my angels. We're not going to be doing anything new today. All we're going to be doing is using the definition of impulse and the impulse equation. I want to show you how you can use it as a lovely shortcut. So remember we said this. We said that impulse was defined as change in momentum, and one way to find it was force times time. Impulse, change in momentum, is also final momentum minus initial momentum, and that's because change in anything is always final minus initial. And then also because momentum is mass times velocity, I can turn this equation into mv final minus mv initial. And because this is final minus initial, which is change in anything, another way to write that last equation, this final equation, is just mass times the change in velocity, because change in velocity is final minus initial, and if I multiplied it out, I would get that. So we're really going to be mixing and matching. Now, you can survive without the impulse equation by simply using F equals what, ma, and Vf equals Vi plus At. But the nice thing is the impulse equation often allows you to do in 1 or 2 lines what might take you 3, 4, or 5 lines of work. So it's a lovely shortcut. And it's going to help us explain stuff about collisions. Let's look at example 1. A force of 8 newtons acts on an object for 10 seconds. So right away I notice I have a force, I have a time, and it looks like I have a mass as well. So A says, what's the magnitude of the object's change in momentum? The reason I said magnitude, remember, change in momentum is a vector, and all vectors have magnitude and direction, but I didn't give you any direction in this question, so I'm just asking for the size, how big. So change in momentum is another word for impulse, so I would write change in momentum, and then I would ask, which one of these 3 versions, sort of these 4 versions, am I going to use? Well, the fact they gave me a force and a time, I'm going to use that one. So it's going to be 8 times 10. Hey, I can do this in my head. 80, and then I'll put a period to make it to 2 sig figs. Heck, I'll even go to 3 sig figs. And you could say kilogram meters per second because momentum and change in momentum are both measured in kilogram meters per second. But since I went force times time, I'm going to use Newton seconds, which are also another way to measure momentum and impulse. B asks, what's the magnitude of the object's impulse? I just found it, because impulse is another word for change in momentum. Done. C says, what's its change in velocity? Okay, this is asking me to find the delta V, the change in velocity. Here, I'm going to use this version. Now, by the way, I should point out on your formula sheet, really what we're using here, I haven't copied your formula sheet here yet. Let me pause the video for just a second. Jump to here. On your formula sheet, what we're using right now is this row right here, and this is the impulse equation. It's mass times change in velocity, which ends up becoming mv final minus mv initial, because change in anything is final minus initial. So if you want me to find the change in velocity, I can say, well, impulse is mass times, not velocity, times the change in velocity. And if I get the delta V by itself, what's the m doing to the delta V? Multiplying, so I guess I'll divide it over. Change in velocity is the impulse divided by the mass. Now the impulse was 80, the mass was 4, so the change in velocity was 20 meters per second. This doesn't mean that the final velocity was 20 meters per second. Here's what it means. If we were initially going 3 meters per second to the right, our final velocity would be 23 meters per second to the right because we changed by 20. If we were initially going 1 meter per second south, our final velocity would be 21 meters per second south. Oh, in fact, D, if the final velocity was 12 meters per second north, and our change in velocity was positive 20, what was our initial velocity? If we're assuming that north is positive, then I think our initial velocity must have been 8 meters per second south. We were going south at 8 meters per second. We changed our velocity by positive 20 meters per second. Now I'm assuming that north is positive for this. So 12 meters per second. Example 2. Again, they want me to find the change in momentum or the impulse. So I'm going to write that down. And then I'm going to ask, which version of the impulse equation am I going to use? Well, they gave me a mass. They gave me a time. They gave me a velocity. Ooh, you know what? They gave me a VI and a VF. So I'm going to use mv final minus mv initial. Really, the way I wrote it on your formula sheet, because I tend to abbreviate, I wrote it as delta P equals m delta V, but since change in anything is final minus initial, the change in velocity would be V final minus V initial, and each of those would be multiplied by an m. Okay. Mass is 350. Final velocity is 18. Is there a direction change at all? I don't see one. Really, what we're finding is the magnitude of the impulse. Minus 350 times 2.5. Sorry for the cough in your ears. $350 times 18 minus 350 times 2.5, and I get 5,425. Double check my writing, looks good. So what did I say it was? 5,400. I'll go to 3 sig figs. So the impulse, the change in momentum, is 5,430. Now you could write Newton seconds if you wanted to. I won't take marks off. Here, because I actually went mass times velocity, I would probably, without even thinking about it, write my units as mass times velocity. I would write kilogram meters per second. So if you're wondering why I flip-flop, it's probably whatever units I used to multiply together to get the answer is what I'll write in my final answer. Ooh, B, what's the magnitude of the force that acts upon it? Okay, so now they want me to find the force. One way to do this, don't write this down, I could go F equals ma, and then I would say, well, I need the acceleration, and I could say, well, they told me VF, they told me VI, they told me T. I can find A. I can go A equals VF minus VI over T, and then I can walk over to here. But you can see this is a several-step question. One of the nice things about the impulse equation is it lets you often do questions in 1 or 2 lines instead of 3 or 4 lines, because I just found impulse, and another equation for impulse is force times change in time. And so they want me to find the force, okay? To get the F by itself, I'll divide the delta T over. Time is always a change in, and so we often get sloppy and don't put a delta in front of it. The impulse we just calculated, I'm going to use 5,425, the non-rounded off version. The time is 60, and you can see, without even bothering to find the acceleration, I was able to get straight to the force. That's why the impulse equation is lovely. It's a lovely shortcut. It's going to be this divided by 60 seconds. It was 60 seconds, wasn't it? Yes, it was. And I get 90.4 units. It's a force newtons. If I'd given you a direction of the impulse, then I would also know the direction of the force, but I didn't give you that. Example 3. By the way, remember at the beginning of this lesson I said I wasn't going to teach you anything new? I hope so far you haven't learned a thing. Maybe I've just clarified some stuff. Number 3, a rocket of mass, blah, 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 starting from rest. Okay, there's a VI. I'll probably mentally or actually underline from rest. VI is 0. Is acted by a net force for 120 seconds. Okay. It wants the final velocity of the rocket. Don't write this down. One way for me to do this, I could go, well, F equals ma, and I could find A, because I have a force and I have a mass. And then I could say VI equals, VF equals, A equals, and I could find, T equals, and I could find VF. But with the impulse equation, I can do all of this in one step. By writing, I know that impulse equals impulse. Don't write that down. You can if you want to. But what I really mean is mv final minus mv initial equals force times time. And I've stopped writing the change in because we get kind of lazy. So I know it's delta t. Oh, and even better, since VI is 0, what I really have is mv final equals force times time. How would I get the v final by itself? What's the m doing to the v final? Multiplying. So divide. And you can see one line and I'm done, as opposed to several lines of work. Again, you can absolutely survive Physics 11 without the impulse equation, but it's sure a nice shortcut. And I will be asking you to find the impulse, so you need to know what it means, that it's the change in momentum, that change in anything is final minus initial, so I can find it by going mv final minus mv initial, or force times time. The force, it says, is 2.3 times 10 to the 4th. The time, it says, is 120 seconds. The mass, it says, is 2.6 times 10 to the 4th. And I get a final velocity of, I think I'm right, looking for typos, looks like 106 meters per second, 106.15, blah, 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 blah. I'll go 106 meters per second. Okay. I can use a similar trick for number 4. So number 4, they want me to find the force. Don't write this down. I could go F equals ma, and then I could find A, and then I could find the force. Or, because I notice that we're giving time, and it wants a force, and I see a velocity, and I see a mass, I can use my impulse equals impulse. I can say that force times time equals mv final minus mv initial. Ooh, and it says bring the car to a halt. So v final is 0. They want me to get the f by itself. How would I move the t over? What's the t doing to the f? It's multiplying, so I would divide, and I'll get here the force is negative mvi over t, which is negative m, 1600, vi, 32, over 1.6. I think I can do that in my head, because I think the 16 and the 1.6 are going to roughly cancel. I think it's going to be 32,000 negative, but let's double check that. Negative 1600 times 32 divided by 1.6. So what's the negative telling me? Well, in the opposite direction of the initial velocity. And that's kind of a Captain Obvious. To bring a car to a stop, yeah, you do have to push in the opposite direction of your initial velocity to slow a car down and bring it to a stop. So this means here, in the opposite direction of VI. So if I had told you a direction in this question, you could actually find the force, both magnitude and direction. Example 5. A rock falls from the top of a 40-meter high building and it strikes the ground below. What's the force, magnitude, and direction of the ground acting on the rock if it comes to a stop in 0.35 seconds? Okay, again, I could find this using F equals ma and Vf equals Vi plus At and all that, but they want the force and they gave me a time, and that's usually my trigger. If the question mentions force and it also gives me a time, then I think, I'll bet you I can use the impulse equation and save myself some time. So I'm going to start out by going F times time equals mv final minus mv initial. And we're coming to a stop. So V final is 0. Problem. I don't know V initial because I don't know how fast I was traveling when I hit the ground. So I'm going to make a little note here. On the left, this is going to be hitting the ground. On the right, we're going to be in free fall. And I think how fast I hit the ground at my V final in free fall is going to be my V initial when I start coming to a stop after hitting the ground. Is that okay? So I'm going to walk over to here. This is good review. Now we are going to use kinematics. I'm going to say, okay, I want to find V final when I hit the ground. I know that in free fall, A is negative 9.8. It does say dropped, so VI is 0. And D equals, remember, I'm ending up below from where I started, so it's going to be negative 40. Which equation can I use? Which equation has a VF and A, a VI and a D in it? I think VF squared equals VI squared plus 2AD. Ooh, and VI is 0, so how to get rid of a squared? I'm going to square root. VF is going to be the square root of 2 times negative 9.8 times negative 40. 2 times negative, 9.8 times negative 40, square root, answer button. Ooh, by a fluke it works out evenly. 28 meters per second. Now, technically, this is negative because it's traveling downwards if we wanted to include a direction. This is that situation where we used our square root button and our calculator assumed we want the positive answer, but in this case, we actually know we want the negative answer, so we know better. But here's what I think. Well, okay. If we let down be negative, let's see what we get over here. And remember, the final velocity right when we hit the ground is the initial velocity when the ground starts bringing us to a stop. We'll get this. First of all, it wants the force, so I'll divide both sides by t. I'll get F equals negative mvi over t. I'll get F equals negative m 2.5. VI negative 28 all over 0.35. And you'll notice I get a negative times a negative, which is a positive. up is positive. Yeah, that makes sense. When the ground is bringing this rock to a stop, it does have to apply a force upwards. In fact, if we did a free body diagram, it's applying a normal force upwards to bring the rock to a stop. So I'm going to get 2.5 times 28 divided by 0.35. I knew the negatives are going to cancel, so I didn't bother putting them on my calculator because I tend to abbreviate. And I get a force of 200 newtons. Again, this left-hand section here, finding the force, I could have actually found the acceleration when we're hitting the ground. I could have calculated that and then gone F equals ma, but this allowed me to do it in one line. As soon as you see compass directions, east and west, we need to realize that we're going to need to let one way be positive and one way be negative. Okay? I don't care which direction you use. You can let east be positive and west be negative. You can let west be positive and east be negative. Gotta be honest, I have a habit of letting the final velocity be positive, and I'll show you why that is in a second here. But for now, it wants us to find the final velocity, so we don't know. I'll let east be positive for now. So this is going to be positive, and since the force is to the west, that 350 is going to be negative. It wants me to find the final velocity. Again, because I noticed they gave me a force and they gave me a time, I'm going to use the impulse shortcut. I'm going to realize that force times change in time, except we get lazy and we stop writing the delta because we're lazy and we tend to abbreviate, equals mv final minus mv initial. Now, we've done this before, but in the previous questions that we did, one of the other velocities was 0 and stuff canceled. This time, nuh-uh. We want to get the v final by itself. What's going to drop down like a domino? I think force times time. Then what? Well, I'll eventually divide by m, but first I would move this mvi over. How will I move this mvi over? Well, it's subtracting, so I would add it over. That equals mv final, and then to get the v final by itself, I would divide by the m. Here is yet another equation for final velocity. Don't try and memorize it. I'm teaching you how to derive these so you don't have to memorize them. Apparently, the final velocity is going to be the force, negative 350, times the time, 0.075, plus the mass, 4.2, times the initial velocity, positive 4.65, all divided by the mass, 4.2. Now, it wants the final velocity, magnitude, and direction. How will I know the direction? If I get a positive answer, east. If I get a negative answer, west. I'm not quite sure. I think we're going to get an answer west, but maybe not. Oh, is there more than one? Is this a fraction? Yes. Is there more than one thing on the top? Definitely brackets around the top. Negative 350 times 0.075 plus 4.2 times 4.65. Close off the top, divided by, don't need brackets around the bottom, and I get negative 1.6. Which is 1.6 meters per second west, because we let west be negative. So this ball hit the wall and bounced backwards off the wall. Not very fast, because it came in at 4.65. It bounced off at 1.6. I can even tell you probably this ball is a little bit flat if it's an air-filled ball. It doesn't have much air in it. Example 7. Rifle accelerates 12 gram. Nice try. Gram. 12 grams is 0.012 kilograms. From rest, okay, there's my VI, to 250 meters per second. There's my VF. It's about 0.85 meters long. Find the impulse acting on the bullet. Okay. I don't see a time force. You know what? I think here, to find the impulse, the change in momentum, I'm just going to go mv final minus mv initial, and I'm going to smile and say v initial is 0 from rest. So the impulse magnitude is 0.012 times 250 meters per second. Works out evenly, amazingly. We get an impulse of 3.0 kilogram meters per second. B wants the force. I would love to go impulse equals force times the time, but I don't see a time anywhere, so I'll put this back in my back pocket and come back to it maybe. You know what? I think I'm going to have to find the acceleration. VI is 0. VF is 250. Oh, and they gave me a distance, which I haven't used yet, of 0.85 meters. I can use VF squared equals VI squared plus 2AD. So to get the A by itself, A is going to be VF squared minus VI squared all over 2D. It's going to be 250 squared minus 0 squared. Didn't really need to write that. All over 2 times 0.85. 250 squared minus 0 squared, which is kind of pointless, divided by bracket 2 times 0.85. I don't think the times kicked in. 2 times 0.85. And I get a big acceleration, which made me nervous at first, but then I said, wait a minute, it's a bullet. Yeah, it should have a big acceleration. So I get 36,000. If I go to 3 sig figs, the 7 would become an 8. It's 36,800. And it's an acceleration, meters per second squared. Now I'm not done. They want me to find the force. Now I could walk back to the impulse equation, but you know what? Since I have the acceleration, I can now just go F equals what? MA. And it was 12 grams or 0.012 times A. I'll write 36,800, but you know I'm using my answer button. So it's going to be 0.012, 0.012 times my answer button. And I get a force of 441 newtons. So this is one time I used the impulse equation for part A, but for part B, this time the impulse equation wasn't a shortcut. This is also why I said you can survive without the impulse equation pretty well for finding forces. It just sometimes saves you time. Example 8 says, consider the diagram at the right for the next 3 questions. The diagram depicts the initial and final velocities of an 800 kilogram car, so the car is identical for both case A and case B. In case A, the car rebounds after the collision. In case B, the car hits the wall, crumples up, and stops. If we assume that the collision time for each collision is the same, which case does the car experience the greatest momentum change. Now, I'm tempted to say, well, here V final was 4 and V initial was 5. Here, V final was 0 and V initial was 5. And so you might be tempted to say something like this. Well, I know that impulse is mass times change in velocity. And you might be tempted to say for case A that the change in velocity is 1, and for case B that the change in velocity is 5. Except we have a change in direction here. So I need to let one way be positive and one way be negative. One way be positive and one way be negative. And remember, change in anything is final minus initial. So for case A, the change in velocity is negative 4 minus positive 5, or negative 9 meters per second. For case B, the change in velocity is final 0, negative 0, minus initial 5. You know what? Case A has the bigger momentum change because case A has the bigger change in velocity. That also means that case A has the larger impulse because impulse is change in momentum. And part I asked for which one had the biggest change in momentum. The impulse encountered by the 800 kilogram car in case A has a magnitude of, well, we can figure it out by going mass times change in velocity. So it's going to be 800 times negative 9. The magnitude is 7,200. So, you know what? Bouncing off of a wall and rebounding definitely does more damage because there is a greater impulse, a greater change in momentum, which means there must have been, is there part E? No. I can tell you, since the time is the same, this must have experienced a much, much larger force. Oh, example 9. This is what I was thinking. Which type of collision is worse for a passenger? Assume that the initial velocities and the time of impact are the same in each situation. So what's worse? A head-on collision in which the two cars stick together and come to a stop? Or a head-on collision in which the two cars, that should say in which, not in when, in which the two cars rebound apart on impact? Oh, you know what? Once again, we're going to vote. How high you hold your hand up is how sure you are of the answer. Now, I know where you're watching this right now. You're thinking to yourself, no one's going to see me raise my hand or not raise my hand, but I'm going to challenge you. Raise your hand or don't raise your hand. Raise your hand for the appropriate answer. Look around sheepishly if you want to, but here we go. So you're going to vote. Are you ready? So situation number 1, a head-on collision where the cars stick together. Who says, oh, that's way worse because they came to a stop? Who says that? Put your hands up. Okay. Okay. So some of you voted for that one. Who says, oh, Mr. Dueck, a head-on collision where they bounce apart, where the cars rebound apart? Ooh, okay. Oh, some of you have your hands way up. What's the correct answer? Well, those of you that picked answer 2 are correct. Why? Well, remember, impulse is mass times change in velocity. So situation 2 has a larger change in velocity. Now, I typed that. You can certainly instead write has a larger delta V, which is what I would write. Example 10. The diagram below depicts the changes in velocity of a ball that undergoes a collision with a wall. Indicate case A or B, which one has the greatest change in velocity, the greatest acceleration, greatest momentum change, and greatest impulse. Well, momentum change and impulse are the same thing, so those should end up being the same answer no matter what. Let's see. What's my change in velocity here? Well, if I let to the right be positive and to the left be negative, to the right be positive and to the left be negative, and I use that change in anything is final minus initial. The change in velocity here for case A, let's write it, I got room right here. The change in velocity for case A is -5 minus 10, it's -15. The change in velocity for case B is -28 minus 30, it's -58. Oh, definitely case B, and by larger we mean bigger magnitude. Explanation, we calculated it. Which one's going to have the biggest acceleration? Well, since acceleration is change in velocity over time, also definitely B is going to have a bigger acceleration. Oh, and because it's got a bigger change in momentum, in velocity, it's going to have a bigger change in momentum, which means it's also got a larger impulse. So the answer here is B, 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 B. I said at the beginning of this lesson, I hope you don't learn anything new. I hope you don't. Now, I'm going to really shorten the homework. However, if you're taking Physics 12 next year, I would encourage you to try every question. And in the homework solution key that I send out on Wednesday, I will include the solutions for every question. But I don't want to give you, normally for this lesson, I would actually have given you all of the homework, and then I would have made the next class a work period just to work on the homework, because the lesson went really long because I wanted to do lots of different examples. So for now, bare minimum, I think you can try 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a lot. Well, it's all really one question, just continuing. Okay? 12 is good, 13 is good. Well, let's see. I'm going to assign a few of these. Uh, 14 is good. I'll skip 15 because I think it's really similar to number 13. 16 I'm going to skip. I don't like that one either. Water skiing, 17 is good. 18 is good. 19, here's the rifle question that we did. 20. Key to notice with number 20 is there's definitely a change in direction. I would let up be positive, and I would let down be negative. Calvin and Hobbes is fun, but I'm going to skip Calvin and Hobbes. But I am going to give number 22. You can skip 23. Again, as before, I will email out solutions on Wednesday, and I'll include another Whoa Wednesday YouTube optional bonus assignment, and you can use that to replace a missing assignment that you have. By the way, if you are not able to figure out which assignments that you're missing, to access my class, email myclass@sd42.ca from your school district email address, and they can reset your password if you've forgotten your password and give you access. I am keeping my class up to date. Generally within a day or two of you sending me something, I'm entering it into my class, and that way you can see if you're missing anything. That's also the only way I can tell you what percent you're at. Even if you ask me for a printout, the problem is the printouts do the percentages wrong. My class calculates it correctly, and you're looking for your cumulative grade when you log into my class. My angels, I miss teaching all of you so much. I hope you're doing well. I hope you're safe. If you have any questions or concerns, or you have a science question, or you just want to nerd out, again, feel free to give me an email. If you want to do a Zoom chat, let me know, and I'll happily do a Zoom chat with you too. Take care, my angels.